Okay, so here's what we have. We have the same setup as we did in section 6.1 and 6.2. We're trying to approximate the solution to a differential equation. And here's going to be our setup. We're going to find case of 1. Case of 1 will be f at our current x and y value. Case of 2 will be f at x sub n, our current x value, plus half a step, and y sub n plus 1/2 hk1, where k1 is defined above. K3 will be f at our current x value plus half a step, and the current y value plus 1/2 h times the k2 that we just figured out. Keeps going. K4 will be f at the x value that we're trying to find, and our previous y value plus h times k3.
Why does it shift like that?
Why does it shift like that all of a sudden?
Yeah. Why does it jump?
Because what we're doing here is we're finding this is a predictor, so we're predicting what's going to happen at the next step, and we're computing what's happening at the current step. So this is again a predictor corrector method is what they would call it. Oh, we're not done yet. K is f at our next x value, the x value that we're trying to find. Oh no, I'm sorry, that was K4. K is 1/6 times K1 plus 2K2 plus 2K3 plus K4. And then finally, to find your next y value. Your next y value is your current y value plus h times k. So notice that at each step, how many calculations do you need to do? 1, 2, 3, 4, 5, 6. At each step, there are 6 calculations. So if I only asked you to do 2 steps, you would have to do 12 calculations. Where if I asked you to do the method from section 6.1, if I asked you to do 2 steps, how many calculations do you have to do? 2. Which one's less work to do by hand?
Definitely 6.1.
Definitely 6.1.
So it's more accurate.
The advantage of 6.3 is at 2 steps we will get a much more accurate answer.
Would this be more efficient for computers to do as well?
Absolutely, this is more efficient for computers. You can get, maybe by doing 4 steps here, you will get the same accuracy of doing maybe 50 steps of the original method. So total number of calculations will be less to get the same degree of accuracy. Seth?
That's H, K, not N, K, right?
That's an H there, that's correct. That's an H. All right, so let's just run through one of these, see how it works. Y prime equals, anybody have a suggestion for a differential equation? 3x plus y. And we need an initial condition. Let's say y at 0 is 5. We want to approximate y at 1. And how many steps do we want to do? 1?
2.
Let's do 2. All right, so n equals 2. If n equals 2, that means h is 1/2, because we're starting at 0, we're ending at 1, we're going to do it twice, so we take a half a step each time. Okay, so K1, I'm going to want a calculator. Okay, so I'm going to have let's see, x0 and x1. x0 is 0, x1 is a half, and x2 will be 1. And then to find y1, I'm going to need to find a k1, a k2, a k3, a k4, a k, and then finally I'll be able to find the y1. And then I'll need all those same things to find y2. And y0 we know, y0 is 5. We picked 5. Okay, so k1. To find k1, I take, it's hard to see all of this at the same time. Okay, so to find k1, I take my current values, which are 0 and 5, and I plug them into my function. So when I plug 0 and 5 into this function, I get 5. Okay, to find k2, I take my current x value plus 1/2 h. 1/2 h is going to be a fourth, and I'm going to plug it into this function, so that's going to be 3/4 plus, and then I take my current y value. My current y value is 5, and I take a half times h times k1. Well, 1/2 is 1/2. H is a half, so a half times a half is a quarter, and k1 is 5, so that's 5/4 plus my y value, which was 5, so that's 5 and 5/4. So it's 3/4 plus 5 plus 5/4. That looks like it's about 7. Okay, to find k3, I take my current x value, which was 0, plus a half times a half, that's a quarter, and I got to plug it in. A quarter times 3 is still 3/4. Plus, I take my current y value and I plug it in, that's 5. Plus, now I have to take 1/2 times 1/2, that's a quarter, multiply it by k2. K2 is 7, so that's going to be 7/4. So that's 10/4. 10/4 is that's 10/4, which is 5 halves. That's 2.5. 2.5 plus 5 is 7.5. Which I might write as 13 halves. Okay, now to find k4, I take my next x value. What's my next x value? 1/2, and I plug it in. So that's going to be 3 halves. Plus, my current y value is still 5, plus h is a half, k3 is 13 halves, so that's going to be 13/4. Alright, so 3 halves plus 5 plus 13/4. I got 14. No, that's not right. Yeah, it
You
is.
just did 3 halves and turn it into quarters. 6/4 plus 13/4. 19, so 39/4 is really
Oh, I've typed in 13 halves there, not 13/4. 27 over 4? Nope, still not right.
39 over
39 over 4. If only this calculator knew what I wanted to type and not what I actually typed. 39 over 4.
And then that would be artificial intelligence, and we'd be in trouble.
Well, we'd be in trouble. All right, so to find k, I'm going to take 1/6, and I'm going to multiply it by my k1, which was 5, plus 2k2, that's going to be 14, plus 2k3, that's going to be 13, plus my k4, that's 39 over 4. I get 167 over 24. How much? No, I got 6.958333333.
You're supposed to add them all up and then divide by 6, right?
And then divided by 6.
Oh, oops, I forgot the 2.
So I got 167 over 24 when I added them all up and divided by 6. All right, so finally I'm ready to find my y value. My y value, I take my current y value, which is 5, and I add 1/2 times 167 over 24. $407 over 48. 48 is what I got.
Oh, wow.
All right, so that was step number 1. Now what do? We do it all over again, except now it's going to be kind of gruesome because now every time we need an x number, we're going to use a half, and every time we need the y number, we've got to use 407 over 48. So it gets pretty gruesome here. Okay, so K1 is going to be K1, I just take my two current numbers and I plug them into my function. So that's going to be 407 over 48 plus 3/2. I get 479 over 48. K2 is going to be our current x number, which is a half, plus a half times h. A half times a half is a quarter, so I have a half plus a quarter. What's a half plus a quarter? 3/4. But then when I plug that in, I've got to multiply by 3 again, so that's going to be 9/4. Plus our current y value, which is 407 over 48, plus 1/2 times h, which is a half. A half times a half is a quarter, times K1, so that's a quarter, times 479 over 48.
George?
Yes?
We made a mistake. 7.5 is not 13 over 2, it's 15 over 2.
Yeah, your answer should be 7.2916 would be.
Oh my gosh.
This is why this is not on the final.
This is why this is not on the final. That's correct. Because what happens when you make one earth mistake right here?
It just falls. Everything else?
Everything else is wrong.
Let's just keep going.
Let's
Just
use
keep
the
going.
numbers.
Two numbers right. Keep going.
Let's wrap up the class.
Well, you get the idea of what you would do, right?
Yeah.
Yes, use 6.1.
The moral of the story is,
Don't do this by hand.
don't do this by hand. What do you do?
George's program.
Let's see, our function this time is 3x plus y. 3x plus y. And then you create a program. Number of steps, 2 steps. Initial x, 0. Initial y, 5. Final x, 1. And the calculator tells you after 2 steps the answer would be 15.7388, accurate to 4 decimal places.
That was pretty quick, actually.
Well, it only computed 2 steps. right?
Imagine something.
Let's say we wanted to do 10 steps. And we're still going to start at 0, 5, and we still want to go x equals 1. What was our answer after 2 steps?
15.
15 point something?
Yeah.
And after 10 steps, it's still 15 point something? Well, let's write. Just compare them. 15.746. That's what we had after 10 steps. Oops. Break. Number of steps 2. 0, 5, and 1. 15.739. So, after 2 steps, we got 15.739. After 10 steps, it didn't get a whole lot better, did it? So it gives you the idea of the power behind this. It doesn't take very many steps to get a pretty accurate answer. What's that?
So long as we're not doing particle physics. Yeah.
All right. Let's try one more. How many steps? 100?
Sure. Yeah.
You've got
0,
time. You've got half an
5,
hour.
1.
This was slower than the other one.
But you can see it pausing a little bit at each step as it does all of the calculations. After 100 steps, we had 15.74625. So after 100 steps, it was no more accurate. It was, well, after 10 steps, we were already accurate to 3 decimal places. After 100, we didn't gain much more. Should have written down what it was after 10. Seven, 15.74624. So after 10 steps, it was already accurate to 4 decimal places. Almost 5. That's pretty amazing. So from a computer's programming standpoint, this is much more efficient than either of the other 2 methods we did.
When would you need to calculate that in a computer program?
Well, when you would need to do it,
There will be a scenario in which you need to use
that equation, of course, we can solve by hand. That one happens to be a linear differential equation. But again, if I gave you this equation, I think I wrote something like this down the other day. And I know some people even went to Wolfram Alpha and tried typing that in, and it didn't solve it. So the best you could do there is to approximate an answer. So again, if I gave you x at 0 is 5, and I wanted to find x at 1, this could do it. I got to go change my function. Oops. Change my function. My function is now cosine x plus ln of y.
You saying our TI-84s are smarter than the internet?
No.
Okay.
What I'm saying is your TI-84 can approximate the solution. And there's 10 steps, and as we saw from the previous one, 10 steps is probably pretty good. It's probably accurate to 3-4 decimal places. Good enough for a lot of things if you're accurate to 3 decimal places. Not everything, but a lot of things. I'm sure there is program into Wolfram Alpha these techniques. I just don't know the syntax for accessing it. But I'm sure it's there. And of course, Wolfram Alpha, the calculations would go even quicker than the calculator does. But calculator's not bad.